first things first. So the first thing I want to talk about integrals involving inverse trig functions is that we're not finding the integrals of inverse trig functions. Okay, we're not finding integrals of inverse trig functions. We're finding integrals of functions that will become inverse trigonometric functions. So that's why we have to recognize that anytime you see a denominator that has the square root of a constant minus a variable squared, you should recognize from our last section that that looks very similar to the derivative of sine inverse. When we see a variable plus a function squared in the denominator, that looks very similar to x squared plus 1, which resembles in some way a tangent inverse function. When we see a denominator that has the square root of a function squared minus a constant and an extra factor of x over here, then notice that that resembles the derivative of secant inverse, okay? So that's why when we see these forms, we're going to try to fit these forms to look like a certain form so that we can recognize that looks like sine inverse, that looks like tangent inverse, that looks like secant inverse. Now what's kind of interesting about this is that this is the first section of 1.7 or the first page of 1.7 in your book. I don't see cosecant inverse, cotangent inverse, or cosine inverse. Why is that?
Because those are just negatives?
Yeah, because notice that the only time that we ever get cosine inverse, cotangent inverse, or cosecant inverse is if we saw a negative up top. I don't think I can draw on this right here. I can't, but maybe I can. Yeah. No, maybe not, whatever. All right, so the only time I'd ever use that is if I saw a negative attached to this, but if there was a negative, why not just pull it out? So that's why when you're going backwards, you're only ever going to get sine, tangent, or secant inverse. You'll never get cosine, cotangent, or cosecant. So far, are there any questions on that idea? Okay, so what I want to first of all just discuss here is just this first example, and then we're going to do one together, okay? So this is a very basic one just to get you used to this whole scheme of things here. But we're first of all going to look at this function up here. And I'm trying to say, if I'm trying to find the integral of this function, that's saying there is some function that I take the derivative of and get to this function. Okay, there's some function I take the derivative of to get to the square root of 1 minus x squared. Well, hopefully you recognize that as sine inverse of x. So the integral of the function is sine inverse of x, and now all we're going to do is evaluate it from 0 to 1. So we apply our fundamental theorem. We take sine inverse of 1 minus sine inverse of 0. Now the question is, what does 1 represent? When I'm calculating sine inverse of 1, what exactly does 1 tell us?
The range of sine.
It's the range of sine. It's not quite the range of sine, but you are right that it is the y value of a sine value. So what does 1 represent?
Amplitude?
An amplitude. It describes a ratio. It describes the ratio, and I'm trying to find the angle that gives me a sine value of 1. So in other words, I'm saying sine of what angle gives me an answer of 1?
Pi.
This is actually pi over 2, because sine represents the y coordinate. So when is the y coordinate 1? Up at pi over 2. What about sine inverse of 0?
Either 0 or pi.
Yeah, it's 0 or pi. But now what's important here is to recognize the range of the inverse trig functions. I'm not going over that. That's part of trigonometry. So I do encourage you to take a look at the video from that I posted on this from yesterday, so you could see that. We're only using values from negative pi over 2 to pi over 2. So that's why sine inverse of 0 is 0. Pi over 2 minus 0 gives me an answer of pi over 2. So the idea of integrating to get trig functions is what we're really working on here. All right, so we're going to go ahead and do an example here. Okay. All right, so we're going to start off with this example right here. The integral of 1 over the square root of 4 minus 9x squared dx. Now, sometimes dx will be in the numerator. It means the same thing as just pulling the dx out and saying 1 over, okay? So we're going to do this in a couple of different methods. But above all, does this first of all should start to resemble an inverse trig function. I see a denominator that has the square root. I see this Pythagorean theorem type of form show up. I see that we have subtraction with the variable coming second. So what does this form resemble most? Sine inverse, tangent inverse, or secant inverse?
Sine inverse.
Sine inverse. What if there was an x out in front?
Oof.
Does that look like secant inverse now?
Secant.
Sure.
All right, not quite. So somebody tell me why it still wouldn't quite look like secant inverse.
Cosecant?
Wouldn't look like cosecant either because that would have a negative.
You have to pull the negative outside of the integration.
It's true, but I'd like you to again refer back to
because it's the constant, the variable are in the wrong spot.
that's right. Look at the difference between sine and secant. Very important. For sine inverse, you see the constant minus the variable. For secant inverse, you see the variable minus the constant. So the only difference is not just that there's an extra factor of u out front, it's that the values of the variable and the constant have flip-flopped. So that's a really important difference between the two. So just by throwing an x on there doesn't change this to a secant inverse function now. Okay? So the point is this starts to resemble an inverse sine function. The problem is that I can only say that it's inverse sine if it looks like the square root of 1, that's not 1, that's a 4, minus something squared. If that's the case, then the answer would be sine inverse of u. So my goal here is to force that to happen. So there's a couple of things you can do here, and I'm going to take you through a couple of options. One thing you can do is to force this to be a 1 by dividing by 4 and divide that by 4. The problem with doing this is that I've divided the bottom by something, but I haven't divided the top by something. So notice that I can't just divide by 4 and say, it's all good. Algebra doesn't allow me to do that. So what would I have to divide the top by?
One-fourth.
2.
2. Now I heard 2. Why did you say you have to divide by 2?
Square root of 4.
Yeah, because what we've really done is we've divided this entire square root. We've divided inside of the square root by 4. So we've got to divide here by the square root of 4. So one thing we've done here is that we've gone ahead and rewritten this. This is now 1/2, so let's pull the 1/2 to the front. And now it's already starting to look a little bit better. Square root of 1 minus something squared dx. So isn't that already starting to look more like the form it's supposed to? The point of what we're trying to do here is force this form to occur. All right, so what exactly is being squared here in order to get 9x squared over 4?
3x.
Close.
3 over 2x.
Yeah, 3x over 2. So didn't I divide this by 4 and this by 4? So notice the quantity here is that I'm dividing by 3x over 2. Okay, so this is one way to do this, starting to make it look a little better. Now, if I'm going to do this, we can again do U substitution or U substitution at this point. So why don't we go ahead and do that by now? See, so the first starting point that I chose to do here was force it to look like 1 minus. So I forced it to look like 1 minus. Now I'm going to use U substitution by letting my U equal the thing being squared. So I'm going to let U be 3x over 2, which means the du is 3 over 2 dx, which implies that dx is 2/3 du. All right, so we could go back here and we could start to replace everything. We've got 1/2. We got 1 over the square root of 1 minus u squared. Dx is 2/3 du, so we have du. Let's pull the 2/3 to the outside. And now what do you notice is nice?
It looks just right.
It looks just right. It looks exactly the way that it's supposed to in order to assume that it's now sine inverse of u. So we're ready to simplify, and therefore, what do we get? Well, over here, notice that we get 1/3 because the 2's cancel, right? And then we get the integral of this function is now sine inverse of u plus c. And now plug it back in, and we get that we function of 1/3 sine inverse of what I chose for u, which in this case was 3x over 2. And there's your answer. Any question on the process there?
Okay, we'll go back really quick. I want to know why like 3x over 2.
You mean, so how did I get from this step to 3x over 2 right here?
Yes.
Yes, okay. So the whole point of this was I was trying to get this 4 to be a 1 so that it fit the form perfectly. So I would have to divide by 4, but you gotta realize here that I'm just gonna do it off to the side here. If let's just say I have 1 over the square root of x, right? If I choose to divide the inside of this square root by 4, then what I've really done is I've divided by the square root of 4 because it's inside of the radical. So that means I would have to divide the top by the square root of 4 as well. So that's first of all why we had to divide the top by the square root of 4. But if we did that, we got to divide every single term. So we had to divide 9x squared by 4 as well. Well, let's take a look at what 9x squared over 4 is. If I rewrote 9x squared over 4 as something squared, then what's being squared to get 9x squared? 3x. What's being squared to get 4? 2, which is where the 3x over 2 came from because it's the quantity. I'm sorry, I keep pointing the cursor, which is where the 3x over 2 came from because it's the quantity being squared.
Oh yes, I understand, but like there is already a 1/2 like before the equation, so I saw it's like 3x.
Okay, so really the 1/2 right here just came from 1 over the square root of 4. I just pulled that out to the front. So that's where the 1/2 came from. So basically all I've done is just a sec here, and let me kind of get rid of all of this. So if we take a look over here, I can probably make this a bit smaller. So this function is exactly the same as getting rid of the 1/2 and putting the 1/2 inside, right? So that function, this function right here, is exactly the same as this function right here. All I chose to do was take the 1/2 from the inside and pull it to the outside, which is now where we end up getting this 1/2 on the outside. And now this quantity right here is u. Okay. I'm going to show a slightly different way here, because what I'd like you to now take a look at that's a little bit interesting, I'm going to rewrite this function. Okay. Okay, we get, let's see here, we get 1 over the square root of 4 minus 9x squared dx. Now, another way to actually do this is to look back to, why does this keep disappearing down here? Looking back to this form. You might notice that sine inverse showed up whenever I had a constant minus a function squared. So it looked like I didn't have to force this a squared right here. I didn't have to force a squared to be 1. I could have made it. Can you see my cursor when I'm pointing at a squared right here?
Yeah.
Okay. So I didn't have to make a squared 1. Apparently, I could have just used a formula to get by using a and u directly. Okay. So let's just go ahead and take a look at what it did. It says, let's write this as something squared minus something squared. And therefore, the integral is just sine inverse of the function over the constant. Let's go back to OneNote over here. Doesn't that mean that I should be able to rewrite? I should be able to rewrite this as the integral of 1 over the square root of 2 squared minus 3x squared. So it looks like I could rewrite this by just writing it as something squared minus something squared. And when I do so, I can see that this right here is representing my a, while this here is representing my u. Right? So apparently that means that I should be able to just use, oh, by the way, I'm missing something here. What am I missing?
du.
I'm missing dx, right? It's still a dx. There is no du yet. Okay. So, all right, well, if that's the case, then it looks like I should be able to just rewrite this as sine inverse of u over a. So 3x over 2. Well, look at that, 3x over 2. Sine inverse of 3x over 2. There's a problem, though, because isn't there an extra 1/3? So the question is, where did I go wrong here? So what would I do to fix this so that now I get what I'm supposed to get based on what the formula said I should get, right? The formula told me that I should be able to get sine inverse of the function over the constant. And I got sine inverse of the function over the constant, and apparently I was wrong. So why am I wrong?
You have to take the derivative of u.
Yeah, because notice that in order to do this, doesn't the derivative of u have to be attached? What is the derivative of u?
3.
3. So
Yeah.
wouldn't that mean that I should multiply by 3 and pull out a 1/3? Booyah. That is where the extra 1/3 comes from. And there's your answer. So we could have done this directly just by using that formula. So the beauty of this is there are multiple ways to do this. This is a great way because it's forcing it to look like the derivative formula. This way, on the other hand, is helping us to recognize that we could bypass that and just recognize the formula that allows us to just take sine inverse of u over a. Is there any confusion on that?
Yes, about the 3 on top.
You're wondering about this 3, where I got that 3?
The green one.
So this is pattern recognition. This is just basically doing U substitution without having to do U substitution. So you could see here that I let U equal 3x, right?
Yeah.
So what is du?
3.
Just 3.
3 dx.
Mm-hmm.
The problem is if all I see is 1 dx, in order to see the du that's necessary, wouldn't I have to multiply by 3? But I can't just multiply a function by 3. So I compensate for multiplying by what I needed by multiplying the outside by the reciprocal. So notice that now this quantity up top is actually du, while now it has an extra factor of 1/3. Another way you could have done it, which is totally fine as well, is you could have physically done the U substitution. You could have said u equals 3x, du equals 3 dx, dx equals du over 3, substitute everything in, and if you did so, that would have given you the integral of 1 over the square root of 2 squared minus u squared times dx, which is du over 3. So there's du, pull out the 1/3, and I get exactly to the same exact place. So if you choose to just do pattern recognition by multiplying by 3 and multiplying by the reciprocal, you never physically have to do the u substitution. Okay? But it's up to you. It doesn't matter which one you choose. All right?
Okay, thank you.
All right. Which means at that point you would have gotten 1/3 sine inverse of u over 2 plus c. And then you would have just realized the u is 3x, and you would have gotten exactly to this point.
Professor, what was the page that you had a few minutes ago that had the different trig?
That's
inverse
actually
curves?
just on 1.7 in volume 2. It's on page
Okay.
108.
Thank you.
Sure. Now, one thing that's kind of interesting here is that sine inverse of this form is just u over a. When you see that the forms over here, it's tangent inverse of u over a and secant inverse of u over a, but there's an extra factor of 1 over a. There's an extra factor of 1 over a. Okay, so all I want to do is just one example with a tangent function just to show you why that ends up happening. Okay, and it's actually going to be a really simple example here. So let's go back to that one.
I have a quick question, if that's okay.
Question.
So I pulled up the textbook on my desktop, and for sine inverse of u over, it's the absolute value of a. Is that okay? Like, we can drop the absolute value?
Yeah, you could drop that because the only, I mean, it technically is the absolute value of a, but if you think about it, it's going to be a constant minus a function squared. So there's no purpose for us to ever write 4 as -2 squared. Right? We would just write it as 2 squared, and therefore we would force that a value to be positive. So technically speaking, it probably should be the absolute value of a, but we would never write it that way, right? We would never write something like, hey, let's change 4 into -2 squared. That just seems pointless. There's no reason to ever do that. So that's why we would always just write whatever that first constant is as the positive value squared? Okay, so that's a good question. It technically should be the absolute value of A. All right. All right, let's do another example here. All right, how about the integral of just a real simple one, 1 over 9 plus x squared dx. Okay, so I'm going to do this the standard way of just trying to force this to be 1. Okay, sorry, I'm to force this 9 right here to be 1. So what would I do to force 9 to be 1?
Divide by 9.
Divide by 9, but if I divide this by 9, I got to divide this by 9, and I've got to divide this by 9, and divide this by 9, right? Which means we're going to rewrite this by writing it as 1/9, the square, or the integral of 1 over 1 plus. Now I'm already getting excited because I love 1 plus functions, because that looks like tangent inverse, okay? And now I'm going to rewrite x squared over 9 as something squared dx, okay?
X over 3?
Yep, x over 3. So I would write that as x over 3. Just out of curiosity, do you see me playing around with the pencils up top?
Yeah.
Yes.
Yeah, cool. All right. Okay, cool. So what would we do at this point then? What do you think we would do to integrate this function?
Let's label x over 3 as u.
Good,
And
so
then
let's
let's
go
try to
ahead and
force it.
call that u. So u is equal to x over 3. Now again, for those that are comfortable with pattern recognition, I am totally fine with you doing that, but it sounds like some may not be. So, so let u equal x over 3. So that means du is equal to 1/3 dx. Which means dx is equal to 3 du.
Professor, just so you know,
Yeah.
if you don't like how your drawings are changing, I think if you unselect ink to shape, that'll fix it.
Yeah, I know. I appreciate that. I can't. Yeah, you're right. I like doing that when I'm like, you know, boxing in answers and circling stuff because it just automatically becomes circles. All right, so let's see here. So if we were to now convert everything, okay, let's take a look at what we got. We got 1/9. All right, we got the 1/9 on the outside already. Okay. We now have the integral of, well, let's see. So x over 3, that's easy. That's that denominator is then just going to become 1 plus u squared. Okay. Dx is 3 du. So we've got du here with now a 3 up top. So if we pull that 3 out, notice that that now means that I have a coefficient of 1/3 on the outside. And now I've got 1 over 1 plus u squared du. So what does that look like?
Tan inverse?
That looks like a standard tangent inverse function. So that means that I could just automatically rewrite this as tangent inverse of u. But wait, hold on. There's an extra coefficient of 1/3. but now we can replace u, and we get 1/3 tangent inverse of x over 3 plus c. Any questions on that? Well, I'm going to go way back to the beginning and just show you how we could have done this in one step. Isn't that nice? So if we were to just look way at the top here, let's take a look at something here. Let's look at how up here, let's see here, at the very beginning of the problem, what if I were to just rewrite this as the integral of 1 over 3 squared plus x squared dx. Again, force it to look like a quantity squared plus a quantity squared. Let's go back to our formula. If I could rewrite the integral as a denominator with something squared plus something squared, doesn't it look like I'm still going to get tan inverse of u over a with an extra coefficient in front of 1 over the constant? I'm going to let that sink in for a minute, because that didn't happen with sine inverse. There was no extra coefficient. But with tangent inverse and secant inverse, it looks like you have to tack on an extra coefficient here. And from the process we just used, you could see why. Hopefully. Notice that my final answer became 1 over a, where a was 3, right? My a value right here was 3. And my u value was x. So I just used the formula, tan inverse of u over a times 1 over a, and there's my answer. So technically, you could literally bypass all of this U substitution business if you just know the formulas. That's why knowing the formulas and recognizing why those formulas are derived in that way is extremely beneficial. Same thing as yesterday. That's why we don't have to use the triangle anymore in order to differentiate inverse trig functions. It's because we already know what those formulas are because we derived them.